In the first part of this lecture, we will finish up closure properties of regular languages. Then we will talk about converting regular expressions into finite automata. Then we'll go through some homework problems as much as the time allows. So there is something that we didn't finish about closure properties of regular languages. So what do we mean by closure properties of regular languages? So now we're trying to review what we did last time. What do we mean by closure properties? So regular languages, what are regular languages? Yes?
A string of symbols.
Okay, so that's a language, any language. What's a regular language? Yes?
It's a language that can be recognized by a DFA or NFA.
Yeah, a DFA or an NFA. Or it can be generated by a regular expression. They are all equivalent, as we will see. We have seen the equivalence of NFAs and DFAs. They recognize the exact same set of languages, but we haven't quite seen the equivalence of regular expressions with finite automata. This is something that we will be doing later, this lecture. Okay? So this is a regular language. Why? Well, maybe to understand what a regular language is, you should see an example of a non-regular language, a language that you cannot recognize using a finite automaton. One simple example is the language L, AN, BN, where n is greater than or equal to 0. So what's this language? AN, BN, this is A repeated n times. As we said in previous lectures, in this course, this is a repetition, how many times you repeat a symbol. So A repeated n times B followed by B repeated n times. So any language in which the string has a certain number of A's followed by the same number of B's. Can you do this with a finite automaton? No, you cannot. If you try to think about it, you will not be able to do this with a finite automaton, because if you think about it, you'll need to count how many A's you have seen. Then you want to make sure that the number of B's is equal to the number of A's. So in a finite automaton, you can't go back. You process the string only one. You have two passes. You take two passes processing the string. So you can't go back to check how many A's and how many. So you should count the number of A's, and then once you start getting B's, you want the number of B's to be the same as the number of A's. And if you think about it, okay, you can have maybe a certain number of states to count how many A's you have seen. But now this will no longer be a finite automaton, because you should do it for an arbitrary number of A's and an arbitrary number of B's. So like if this is 1,000, you can count 1,000. But if for an arbitrary number of A's or B's, you can't do it. So this is an example of a non-regular language. So it's important to see, that not all languages, not all formal languages can be recognized using finite automata. And you can't write a regular expression for this either. Okay, so now closure properties. Regular languages are closed under what? Regular operations, which are union, concatenation, and star. And in last lecture we showed how to how regular languages are closed under union. How did we show that regular languages are closed under union? How did we show that? So we showed that given NFAs for two regular languages, we can always construct an NFA for the union. And same for the concatenation. Given NFAs for two languages, we can always construct an NFA for the concatenation. So, for the union, so let's summarize what we did last time. How does the NFA for the union? How did we construct an NFA for the union? So we're given NFA1 and NFA2. What does the NFA for the union look like? So you just branch.
Two paths.
So if you are given two NFAs for two languages, then this is NFA1 and this is NFA2. And this is an NFA for the union. You can always do this. Right? Now for the concatenation, again, this is the NFA1 and this is NFA2, and you connect them using what? An epsilon transition. What else do you need to change?
Take the accept state off of NFA.
Yeah, exactly. The accept states here will no longer be accept states. The accept states of the first NFA will no longer be an accept state. That's how you construct an NFA for the concatenation of two languages. Now, how do we construct an NFA for the star? So far we have been reviewing materials that we covered in previous lectures. Now the new stuff, a regular language for the star. Now consider this. Let me use the same example that I used last time. Did I use 01 or 10? 01? Doesn't matter, but I just want to be consistent.
It was 10.
Well, it was 10?
Yes.
Okay. Okay, so I used 10. I'm going to redraw. Oh, okay, so I can gain the space here that I need. Okay, so the language where 10 is a what? Is a substring. So it's going to have 01, 01, and this is an accept state. Now we would like to construct an NFA for the star. So how do you think we can construct an NFA for the star? What's the idea in the star?
It can be repeated.
Repeating, yeah, exactly. So the key idea in the star is repeating. So how can we construct an NFA for the star? Yes?
You can put in the epsilon, the backwards 3 kind of symbol, and put it from the accept state all the way to the beginning.
Okay, this is a very good idea. It's a very good start, and in fact, this is almost correct. So this is almost correct. It will allow you to repeat as many times as you want. So this is the key idea, but this is not quite correct. Why isn't this correct? What's wrong with this?
It'll never stay in the accept state.
What's that?
It'll never stay in the accept state.
Or
No, it can stay. See, this is an option. Remember that this is an option. Nothing that's going to force you to take this epsilon transition. It's not mandatory. Yes?
The star lets you repeat the string 0 times, not just 1 time. You can do it 0 times.
Oh, exactly. Yeah. What we are missing is repeating 0 times. Or, in other words, this NFA does not accept epsilon. And accepting epsilon is important. Now, how can we make it accept epsilon? One wrong way of trying to accept epsilon is doing this. This would be one way of accepting epsilon. Yes, it will accept epsilon, but it will screw up everything. Why? What?
Oh, it's not basically anything.
Yeah, this will accept anything. This is an NFA for accepting sigma star. You can accept anything here. You just say this, and this tells you you have always the option of looping in this accept state for any 0 or any 1. So you can choose to stay there for any string, and this is going to accept any string. So it's going to accept sigma star. So this is not what we want. So how do you think we can resolve this and get an NFA that repeats, but at the same time accepts the epsilon without accepting everything in the world?
Making a branch for epsilon, its own accept state?
A branch for epsilon. Yes, yeah, you can do that. Basically handle the epsilon separately,
Yeah.
and we can just add a state for it. So we can just do this. So this is for, if you have an epsilon you accept, and then this is connected to anything else, then you have just this, and you can loop as many times as you want. So this will make sure that you accept epsilon, but it will not accept everything. It will only accept epsilon. If you get a 0 or a 1, you are, you'll have to go to one other state besides this state. You can't stay in this state, and you can repeat. So this will give us exactly what we want. We can accept epsilon, and we can repeat as many times as we want. So this is an NFA for the start. Now let me draw the diagram in general. So in general, it's going to look like this. So if I have a start state, and then some other internal states, and let's say some accept states. So this is general. So what I'm going to do in order to do the star, I'm going to generate a new state, or introduce a new state. Let me call it QS for accepting epsilon. And then I'm going to make an epsilon transition to this state. And then what? What should I do? Epsilon. I need an epsilon, a loop back, or this kind of epsilon that takes me back to the start state, the original start state, not the start state that I added. The original start state. And I need to do it for every accept state. So I need this. Okay. So this is a general NFA for the start of any given NFA. Now let's write it in the formal description, which is everybody's favorite form for describing a DFA or an NFA. I mean, I know that everyone is feels much more comfortable with this, with the graphical representation of an NFA or a DFA. So the formal description is less fun for most people, but some people find it more fun. Okay, so the formal description, given an NFA, let's call it N1 equals Q1 sigma delta Q1 and F1. So this is abstract and general. For L1, we can construct an NFA N for L star as follows. Okay, so N equals Q sigma delta, this is delta 1. Delta Q and F. In fact, I can call this QS, Q sub S, where Q sub S is a new start state that we add. We add Okay? And Q is going to be equal to what? What's the relation between Q for the star and Q for the original NFA? Look at this. So this is Q1. So what's the relation between Q and Q1?
Q union QS.
Yeah, exactly. So Q equals Q1 union QS. What's the relation between F and F1 in this case? The set of,
It's just F, the original, the accept states don't change.
but this is an accept state. So this is an accept state. So it's F1 union QS. So it's also F1 union QS. Okay, so we covered Q and F and QS. It remains to cover delta. And delta of Q and X is defined as follows. Okay, delta of Q and X equals. Now, for which states will delta remain the same? The transition will remain the same for what set of states? So for which states did we make a change?
Just the accept states.
Yeah, we made a change for the accept states. So any state that is not an accept state, we didn't touch it. We didn't make any change to its transition. So if for any original state that is not an accept state, we did not make any change. We only changed the transitions for these accept states, and then we also added a new state. So we should define the transitions for this new state. So it's going to be delta 1 of Q and X if Q does not belong to, or if Q belongs to Q1 but does not belong to F1. So if Q belongs to Q1 and Q does not belong to F1. Now what if Q belongs to F1? Then what we did is adding epsilon transitions when it's for those transitions that have, we added epsilon transitions. Transitions for the epsilon symbol, which is an acceptable symbol in an NFA. But for other transitions, like if this state had A, B, C, we didn't touch these. So the original transitions for any x that is not equal to epsilon remain the same. So it's going to be delta 1 of Q and X if Q belongs to Q1, Q belongs to Q1, or if Q belongs to F1, if Q belongs to F1, and what? X is not equal to epsilon. For any x other than epsilon, there is no change. Now, if Q belongs to F1 and x equals epsilon, what's the change? We are adding epsilon transitions. So this is F1 that we are talking about. This is F1. So if x equals epsilon, what should the transition be? Where are we going? What's this?
Q0 of the.
This is Q1. Yeah, we called it Q1.
Oh.
And this is the QS. So if there is epsilon, we added transitions to Q1, but we did not touch any original transitions that may have existed before. So this may have had some epsilon transitions before. So that's why this is going to be delta 1 of Q and X union the set Q1 if Q belongs to F1 and X equals epsilon. What else do we need to define? Define the transitions for the new state that we have added. So if Q equals QS, but there are two cases for Q equals QS, because the transition may be epsilon or non-epsilon. So if Q equals QS and X equals epsilon, we have a certain transition. And if Q equals QS and X is not equal to epsilon, we have a different transition. Now, what's the transition if X equals epsilon? Where do we go? We go to Q1. So if X equals epsilon, then we go to Q1. That's where epsilon takes us. Now, what if X is not equal to epsilon? Where do we go? Is there a transition? No, there is no transition. And in the NFA, we just say phi. There is no transition. Okay. So this is the formal description of a state that represents the star. Okay. Okay, questions on this before we move to the next topic?